It is 9:01, so I'm going to get started. What we'll do today is to continue our discussion from the other day. And this time, the objective of today is to be able to grab 2 bytes from memory and add those two numbers and get a sum. That's all we're going to do today. Okay, so it doesn't sound like a whole lot, but it is. Okay, because even though we had components that we had created the other day, we are not putting things together yet. Okay, we have individual components. So what we'll do today is to look at this particular file. We had the ALU, so I'm just going to quickly recap what we did the other day. The first thing that we did was an ALU, or logical arithmetic unit. The job of this particular subcomponent is to have 2 inputs, a few control lines, and an output. Okay, so from the input, that's basically parameters into a function, if you will, and then you can select what the function does. Okay, so in this case, I have the ability to add and also the ability to subtract. That's all that I can do. And then what I can also do is to get the output. Now the adder and the subtractor, they operate at exactly the same time. So to choose the operation, you're really just choosing the output of which component becomes the actual output through the multiplexer. So this multiplexer, otherwise known as a mux, is what is choosing the output. So that's the entire usage of this particular subcomponent, is to do calculations. It does not store anything. Okay, there's no storage whatsoever. The pins are not storage devices. So when you look at D in 0 and D in 1, all they are doing is to serve as an interface to other components that we are designing around this thing. D out the same way, and all of the other pins are really just a way for other components to interact with this particular component. Kind of like the input and the output of your half adder, the full adder, and then the entire 4-bit adder that you did for your homework assignment. Okay, so this is the first. This was the first component that we talked about the other day, and then we talked about registers. And the registers subcomponent looks kind of like this. We have control circuits to help us select which register we want to use. In fact, there are 2 ways to select which register we want to use, because we can have simultaneously 2 outputs from this particular module. And 1 input, and then the 4 registers, A, B, C, and D, they are kind of a storage device. They are not memory, but they are also storage devices. They're on chip on the same die as the ALU. In other words, in terms of actual silicon distance, this is pretty close to the ALU. They're right next to each other. Okay, as fast as the ALU can do calculations, the registers can usually keep up supplying information to process and also storing processed results. Do we have any questions regarding these 2 components? No questions about these 2 components? Okay, so what we'll do today is I'm going to add a 3rd component that is not my design, which is memory. Okay, we have all kind of worked with memory before, so we'll add a 3rd component of memory. And then we'll try to determine, how do we get 1 byte from one location, get another byte from another location, store those things into registers, and perform an operation. Okay, like adding those 2 numbers. Okay, it's as simple as that. Maybe we should not even go that far. Maybe we should just get a byte and store it into a register, and then we will store it into another memory location. I think we'll just change the objective to just that. Okay, so the ALU is not even being used. Right. I forgot the row sheet today, so I'm not gonna take row. I actually had it printed this morning. I put it on my desk, and then forgot to put it in my bag here. So it's still sitting somewhere on my desk. But that's okay. All right. So we switch to the main screen here, and then what we'll do is to remove any components here, and then we'll go ahead and select memory, and we'll pick just RAM here, because we are dealing with random access memory. How many people are kind of familiar with the acronyms like RAM, ROM, EEPROM, stuff like that? Okay, so what is double EEPROM? EEPROM.
Electrically erasable read-only memory.
It's you got the first two right, but you forgot about the P. Programmable. Yep. So it's electrically erasable, programmable, read-only memory, which all by itself is a mixture of conflicting words. Okay, because it's electrically erasable, but it's read-only. It's also programmable. Okay, that has to do with it's a long history. Okay, so I'm not going to get into the various types of ROMs today, but I just want to kind of mention that because we refer to RAM and ROM all day long, and I just want to make sure that you guys understand what they stand for. RAM is random access memory, so that means we can read and write to any location. All right, so we have this component, and then we'll go ahead and use one of our components here. In other words, we'll go to registers, or the register subcomponent here, and we'll put it somewhere on the screen here. So now we have two major components, and remember the objective is to read a memory location and then write it to another memory location. That's all we want to do. Okay. Your homework assignment already gives you an idea of how to read and write, but this will also integrate okay, now we're not just reading and writing memory, we also want to utilize the registers. Okay. All right, so we'll put this here, and this is the address bus of memory. In other words, this is the quote-unquote pin. It is actually consisting of 8 individual pins in this case, but these are the pins to specify which location am I interested in. Okay, so we have to somehow be able to specify the location that we want to access in this case. When you're dealing with a processor, there are registers, and sometimes you can use registers to specify which location do I want to access. So that's one path. That's one way to specify where you want to access. But the other way to specify what you want to access is through a special register called the PC, the program counter. Okay, the program counter is basically just a counter. For the most part, it counts up only, but occasionally it can change its value to just about anything. But the program counter can serve as an input, to the address bus to specify, what you want to access. The program counter is kind of special because it's kind of like, okay, if you consider running a program as reading an operation manual, on paper in a binder, the program counter is a bookmark to tell you what is the current page. Okay, so as you execute instructions, when you're done with one, you move on to the next page. So the bookmark, is just kind of increment, go to the next page. When you're done with the next page, it moves on to the next page. So that's what the program counter is a bookmark to indicate where is the next instruction. Usually it refers to the next one. Where is the next instruction to execute? So in that way, it is a very special register. It's not like the other registers where you can say, oh, I want to do an add, I want to do a subtraction, I want to store into a register. This one is special purposed. And as a result of that, I will go to not my own registers, but I will go to memory and use one of the registers from there to represent the program counter. So now we have this as our program counter. Usually it is abbreviated to PC, and that's pretty common terminology. It's not really just something that I use, but it's used in industry as well, with the program counter. Now, I would like to do something like this because it's simple, okay? Like hooking up the output of the program. Let me zoom in a little bit here so we can see a little better. So I would like to do something like this, hooking up the output of the program counter directly to the address bus. But I can't do that. The reason why I cannot do this is because if I did it this way, then the only way to specify an address is to use the program counter, which is not always the case. Okay, because if I always use the program counter to specify which address I want to access, that means there's no way for me in the program itself to control which address I want to access. And also, there's no way to specify which data item I want to access in memory either. Okay, so at this point, you have to remember there are basically two books to use when you're executing a program. One book is the operation manual. Okay, it contains all of the instructions. Okay, do this first, do this next, oh, take note, write down the value of this little dial, or of this gauge here, add 30 to it, and then use that value and dial, the other, control to that value. Okay, that's your operation manual. The other book that you also need, usually, when you run the program, is for data. Okay, that's to store your variables. Okay, so the other book is intended to be written a lot, overwritten, a lot, because you have to jot down little notes like, oh, okay, I can see that the current voltage is 5 volt here, but I want the target voltage to be 20, so the ramp up is going to be this number. So you have to use the data portion to store numbers, values that you'll be changing. Since you're all coming from a cisp310 background or equivalent, the program side or the operation manual side is the C code. It is your control structure. It is your function, and so on. The other portion would correspond to your variables, the data. Okay, it's not just the variables. If you use new and delete in C and C++, but in C++, or if you use malloc and free in C, then it also belongs to the other manual. Are we still doing okay so far? With the analogy. Certain things do not change. It only tells you what to do, and that is not supposed to change. But as you're following the instruction, you also need a scratch pad to write down information that will change over time. The variables will change over time. So you have two pieces of information or two chunks of stuff that you need to access. Now, logically speaking, they are two different things. But in most computer architecture, they belong to the same memory bank. In other words, we use memory for both purposes, to store the instruction to execute and also to store the data that you need as you execute the instructions. Are we still doing okay so far? Okay, so logically you have two binders, okay, or one binder and one scratch pad. But in reality, they're all combined into one single memory space. Okay, now if that is okay, that means, aside from the PC, which is a bookmark of the operation manual, we also need something else in order for us to access data. So I'm going to use another register for that purpose. Now, when we talk about registers, remember, a register is not, it's simply something that can store, in this case, 8 bits. Okay, you can store 8 bits into one register, and you can update that value. Okay, that's all we can do with a register. Memory, on the other hand, is a little bit different because it has a lot more storage location, and you can address it. Okay, you can specify in this particular memory chip, we want to access a particular location. A register has no address. Okay, you specifically say, I want to access PC, the program counter. I want to access register A, register B, register C, and register D. But memory, as a single unit, has multiple locations depending on how big of a memory module you want to deal with. In this case, this particular memory module has an address bus of 8 bits, which means it has 256 locations. And the data bit width, which is 8, means that each location only stores 8 bits, or 1 byte. Are we still doing okay so far? So in this case, this memory module is basically saying we have 256 pages, and each page has 8 bits. And that's the minimum, that's the quantum that you can address. You cannot address individual bits. Every time you address, you get something from this particular memory module, you're getting 8 bits. Every time you store something into it, you're updating 8 bits. You cannot store and retrieve individual bits. Are there any questions about that part? No questions? Okay. All right, so now that we have a separate register so that we can access something other than instruction itself, let's give it a name. Okay, so we'll call this indirect register. Okay. Indirect register simply means we are using the content of this register to indicate which location we want to access. Are we still doing okay so far with that concept? Sort of? Okay. All right. So we want to do something like this. Okay, we want to hook up both of these registers because the intention of both is to specify a location in memory to access. So conceptually, this is what we want to do. We want to say, well, in order to specify a location to access, Sometimes we use the program counter, and other times we use the indirect register. But this is not a good idea. It's not a good idea for one particular reason. If you remember, the registers is always outputting something. Okay, this pin is connected to usually the reset line to reset everything to 0 when the computer starts up. This pin is connected to what we call the clock. So when we see a transition which is low to high, then it updates the register's content from the inside, from the input side, which is the D pin. This is enable, which basically means if it is 0, don't pay attention to anything, but the output is still driven. Okay, and this pin here is the input pin, which means if the register is enabled and the clock is doing a transition, take whatever is here and update the content of the register. A register is somewhat like a variable. You can update it. You can also get this value. But in order to update the content of a register, you have to have enable turned on, being a 1. And while enable is 1, you need the clock line to perform a low to high transition. Then it will clock in and register the input and store that value into the register. How do I turn off the output of a register? Is there a pin here to turn off the output of the register and say, don't drive those lines, and somebody else will be driving those lines? No, there's no control to do that. So whenever you have two components, in this case we have the indirect register and the program counter, whenever you have two components that are both driving the bus or driving these lines, these traces at the same time, and there's no way to disable either one, is bad. Okay? Because it's always possible that the program counter is saying, I want bit 0 to be a 0. And then indirect register says, I want bit 0 to be a 1. Okay? So now you have a bus fight. Okay? You have a fight in the bus. Because one thing is trying to drive it low, and the other thing is trying to drive it high. So it will do two bad things. One is, as far as the memory module is concerned, it doesn't know, should I register bit 0 to be a 1, or should I register it to be a 0? Because it depends on which one is stronger, right? It depends on whether the indirect register is stronger when it's driving high, or whether the PC is stronger when it's driving low. Now, I know the answer to that question, which one is going to win. What do you think? This kind of relies on your knowledge of transistors, so I'm not expecting anyone in this class to know the answer.
Register.
Sorry?
The register.
Say again?
Which one will win? Is that
Yeah,
what you're saying?
the one who's trying to drive it low, or the one who's trying to drive it high?
Drive it high.
It's actually driving low. Most chips, because they use the N material as a substrate, so that makes driving low actually if they can drive more current when you're driving low, when you're sinking current, but when you're sourcing current, it's actually weaker. So most of the time when you have a bus fight, one is trying to drive high and the other one is trying to drive low. The one who's trying to drive low usually wins. But the worst part is it will also damage the parts. Okay, because these parts are not supposed to deal with any large amounts of current. Okay, they're supposed to only drive with a very small amount of current to specify a high or a low, a 1 or a 0. So when you have a short from a high to a low with nothing in between to stop or slow down the current, then it's going to have a big current going from one pin from this chip or from this component to the same pin on the other component. And because these parts are very small and you're dealing with a large current, it will burn out the part. Okay, so a bus fight is very, very bad because it will, it just won't work. So that means, this won't work. Well, if this is not going to work, is there a component that we have already talked about that can help us in this scenario? How can we take the output of two individual components and feed it into one single one? Sometimes we want one, and sometimes we want the other one. Have we encountered something like that? In fact, have we seen something like that just earlier today?
The multiplexer.
A MUX, a multiplexer. Okay, so a multiplexer is also useful for something like this. Now, in terms of actual implementation inside a real processor, sometimes the registers themselves have an output enable, which is nice. Okay, because in that sense, you can actually just say you can just tell a register and say shut up, don't do anything, don't drive the line at all, let it float. Okay, so if you can make a register float, then you don't need a multiplexer, because you can basically just make sure that the rule is, okay, everybody shuts up except for the one that is supposed to specify the address. Yep.
Would you be able to put a buffer on those?
You can put a buffer on those, but that would actually it will put more components into the system than the mux. But you can use a buffer for that. So for simplicity, I'm going to use a mux for that purpose. So we use a multiplexer, and you can see the multiplexer is just the shape of it, kind of implies what it can do. So in this case, we have two outputs combining into one single output here. So you just draw these lines accordingly. So one goes here, and we'll fix the orange issue later, which is the new black, right? Okay, I have never watched a single episode. It's just that Netflix, advertised that show, the heck out of it. It's like difficult to ignore. I just want to watch Chuck. I don't care about orange is the new black. All right. So in the mux here, I'm going to change the data bits to 8 to match the width of the output and also the width of the address bus here. So now I can hook up this one directly to the address bus, and we're good to go. All right. Now the mux also has control lines. Okay, these are called control lines. One is to specify, okay, which input should I select? Should I select input 0 to become the output, or should I select input 1 to become the output? So at this point, I'm going to just make it a pin. Okay, so when you run the simulator, you can just specify the value of the pin in order to control this line here. This is going to be an input pin, so we'll just use this and make it face north. So, and we'll give it a name. We'll just say address bus selection. So it allows us to select which register do we use to specify an address to the memory chip. Okay, so that's good. Next, when the memory chip is addressed, we have the usual stuff. Okay, we have the selection here. So if you only have one single memory chip, yeah, you can just kind of say it is always selected. But instead of saying it is always selected, let me just put a pin here. So I'm going to use another pin for memory select here. So we'll just label it as select, make it face north, and attach it like that. Okay. And then we have the clock, the load, and the clear. The clear line, is going to the reset line here, so that when we start up the computer, everything is going to be cleared to begin with. So along with all the registers, and also, in this particular module, which represents all of our registers, also has a reset line. So all of these lines need to connect to a pin called reset. So we'll go ahead and create a pin called reset. So we'll just call this one reset. And this is a system reset pin. A system reset pin is used, basically throughout the entire design. So anywhere you need something to reset to a particular value, when you start up a computer or you push that reset button, they need to be connected to this reset pin. Okay, and some can be connected indirectly, but most of these, you really should connect it directly. So we'll go ahead and specify the reset pin, on all of the components that we have already talked about that has a reset pin or needs to be reset to known values. Okay. Are there any questions about the reset pin or what it does, overall, just overall speaking, what it does in the system? Now, when you think about this, when you start up a computer, the voltage doesn't just go from 0 to the operating voltage like instant. Okay, it's not a square wave. Okay, power supplies need time to ramp up the voltage. So now the question is, what do we do, or what does the processor do when the voltage is still ramping up and not quite to the real stable operating voltage yet? In other words, when you look at the voltage from your voltage regulator or power supply, okay, so when you look at time and the voltage output from the regulator or from your power supply, ideally speaking, we want to turn it on. It goes like this. Okay, this is the right operating voltage, but it doesn't do that. There's no electronic that can do something like that. Okay, it's just unrealistic, especially when you're dealing with a large current or a power device. Like most processors consume up to tens of watts at least, even with the laptop computers on the regular computer. So there's no way you can actually ramp up the voltage like a square wave. So when you look at time, it's more like this. Okay, it ramps up and it bounces a little bit and then it stabilizes. Okay. So now the question is, when it's still within, let's say, this region here, possibly over here, because you don't want it to be bouncing around when you're using the computer. So when it is within this region here, what do you think your processor should do? It should be held in the reset state. In other words, the reset line that we have drawn here in the design should remain a 1 or asserted throughout the entire time, from the beginning all the way up to the point where the voltage is stabilized. Most designs will give us a little bit more leeway. So even though it is completely stable at this point, most design will put a delay and make the reset period all the way up to here. In other words, it will give us a few milliseconds, okay, after it is stabilized, just to be sure everything is good to go. Because one of the worst things they can do with electronics is having the components to operate at a unintended voltage, or at a voltage where things may go or not. Okay. So that's why when the voltage is ramping up before it stabilizes, you definitely don't want to do a single thing. You want to hold the reset line and just say, don't do anything. Reset to your known state and just stay there. Okay. Once it gets up to a stable voltage, then you disable the reset line, so the components will start to work at that point. Are we doing okay so far with this part here? Yep, go ahead.
What's the increment like for time? Like, what's the scale?
It depends on what you're dealing with. On really, really small devices, like a microcontroller unit, like the processor on an Arduino, the reset period is measured in milliseconds. So it's typically a few milliseconds, like 5 milliseconds, 6 milliseconds. It doesn't sound like a lot of time to us, but to the processor, that is really, really a lot of time. And on most processors, you can actually, it's quote unquote programmable. So the delay to take reset off of the asserted state is actually programmable. So it depends on your power supply. If you have a kind of noisy power supply or inferior power supply, you can lengthen that time. You can also shorten the time if you have a good, better power supply. On PCs, I'm not sure what is the order of magnitude, but I would assume it's longer, possibly up to hundreds of milliseconds, if not more.
Yeah.
So when you from the moment you actually plug in or press on the power button to the time that your processor actually starts to clock and start to do something, that can be like hundreds of milliseconds. But we hardly notice anything like that, because when we press a button, just the mechanical act of pressing a button is long. So we hardly notice that delay when you're dealing with a PC. That's a good question. Okay, so I have just kind of explained what the reset line is, what it is useful for, and also when the system starts up, you need to have some kind of circuitry to keep the reset line asserted until a certain delay, and that circuit is usually called a supervisor, or reset supervisor, voltage supervisor, or something along that line that monitors. It is a hardware component. It's not part of your program. It's not part of the computer, the processor itself. It's usually a separate component, and its only job is to monitor the voltage to your processor, and until it is within a good range, at least up to a certain amount of time, it will hold the reset line asserted. That's the only job of that particular component. Sometimes you have processors having that component built into the processor itself, but most of the time it is outside of the processor. So it's an external chip that has that one simple little job. This is also I know it's a digression, but that chip also would sometimes do something else. So think about what happens when your PC is quote unquote locked up. Okay, in other words, it's not responding at all. It can be a problem with the operating system, can be a problem with the drivers, which is a very common issue when it comes to operating systems. A bad driver can kill the entire operating system. Okay, make it quote unquote hang up. Okay. So the question now is when your operating system hangs up and doesn't do a single thing, there's usually a delay. I cannot remember how long, maybe 30 seconds or so, until the blue screen of death shows up in Windows. Okay. So how does that work? I mean, if your computer is completely locked up, how could it get to the blue screen of death and at least say that, oh, something really, really bad just happened?
It's got to be some type of catch before it.
It's some kind of mechanism external to the processor, that is keeping track of your processor. It's called a watchdog. Okay. Now this part is kind of extra to the content of this class, but since we're already at this level of discussion, I might as well just throw that in too. So it's called a watchdog mechanism. Now what the watchdog is it's basically a timer device. Okay, it's a timer device of sort. The way it operates is, it expects the software, the computer running the software to quote unquote hit it every so often, like every 30 seconds or every 15 seconds or something like that. Okay, if it does not get quote unquote hit or clicked within like 30 seconds or a minute, it's usually programmable, then it will do something. It will usually do an interrupt or a reset depending on how you program it. And bring the entire system out of the quote-unquote locked up state. It's called a watchdog timer, and it's a very useful device, in case your program, your operating system has completely crashed to a point where it is not recoverable. This little mechanism can at least reset the program, reset your entire system from the beginning state. Okay, but that's kind of extra to the stuff that we are currently talking about. All right. Okay, so now we have a few other things to do, like the load line here. We have to kind of specify a 1 is to load the memory to output, which is a read operation. So we'll go ahead, this part you should know already because we talked about this already. So this is called the read line. Now the way I write the read line is also the RD/WR, and let's make the font, the label face south so that we can still see it, and make the pin face north, so this way it's a direct connection to the load pin here. The reason why it's called RD/WR, read/write, is because when you put a slash in front of something, it means it's a negation of that. In other words, if I just write /WR, it means when the pin is low, it is a write operation. When the pin is high, it is not a write operation. It is negating the meaning of that pin. In this case, RD is just fine. /WR is fine too, because we're using one single pin to control whether it's reading or writing, and those are the only two things they can possibly do to a memory chip. So that's why we use the slash symbol here. So what that also means is, on some schematics, you will see that people just use /WR to label that particular pin, because it's basically read as not write. Okay, so when the pin is high, it is not writing, which means it's reading. When the pin is low, not low is true. So when it's low, then it's writing. Am I making any sense? On actual designs, the reset line usually has a slash in front of it too. In other words, when you measure the voltage, when the reset line has a high voltage, it is actually not resetting. It is not asserted. In order to assert the reset line, it has to measure a low voltage. This is also what we call an active low signal, because when the voltage is low, it is active, it is asserted. But in this particular environment in Logic Sim, because it is really designed for people with more of a software background instead of a hardware background, so they don't use active low signal a whole lot, because it's just confusing to people who are just really dealing with software. All right, so we're almost done here. We got one more clock signal here, and the clock signal is doing the same thing as what we remember from previous discussions. So we'll go ahead and specify our clock pin, and we'll just call it clock. Stash it here. Okay. All right, and we have a few pins left. We have this pin here, which is our enable, and we have this pin here, which is also the enable to select either the input register or the either the indirect register or the PC register here. And then we have the data here that has to be connected to something, because this is bidirectional. By the way, this pin here is bidirectional, which means sometimes it is expecting the line to be driven by another component when you're writing to memory. Other times when you're reading from memory, it is driven by the memory chip itself. So that's why it's called bidirectional. The address pin, on the other hand, from the memory perspective, is input only, because it doesn't make any sense for the memory chip to tell the processor, hey, I want you to read location 512. Because it usually makes sense the other way around, right? The processor running your program is going to tell the memory chip and say, hey, I need to get the content of location 512, and not the other way around. So that's why the input pin, that's why the address pin is input only, but the data pin is bidirectional. It can either drive the line or it can sense the line. Okay, it is not active. It is just sensing. It's acting as an input pin. All right. So now with the output pin, this one is also in the design that you guys have dealt with already. So whenever you have a pin that can either serve as an output or an input, you can't really directly connect it to stuff. Okay. So in other words, in this case, we have register. So here, we have register in and register out 0 and register out 1. So ideally speaking, or simplistically speaking, what we want to do is to do something like this. Okay, so this line allows us to go from memory into register. We can read a location from memory and store it into one of the registers that we have already included into that module. And whenever we want to, we also want to be able to output from a register and store the content into memory. But this won't work. It won't work for exactly the same reason that we have talked about a little bit earlier, why the indirect register and the PC, the program counter, cannot be connected to the address bus without a bus in between. Because when two components or two or more components can drive the line at the same time, you can end up with a bus fight. So that's why we can't do it this way. Because the registers, these two lines are both outputs from the register, and the data line here can be output also from the memory chip. So that's why we cannot hook it up directly like this, where this type of diagram or this type of symbol means that they share the same copper on the circuit board. Okay, these pins eventually connect to the same copper, the same conductor, either on the circuit board or on the same using the silicon on the chip design. They're just connected electrically. So we cannot do this. Okay, that's not a good idea. So if that's not a good idea, we have to do something else. If you remember from your homework assignment, we have something to help us, to determine which way things should go, and stuff like that. So that's what we need to do, is to use those mechanisms to control. Okay, these things can go in this direction, and it can also go in this direction, but not both at the same time. Okay. Are there any questions at this point? Questions? But for the time being, let's not take this one into consideration just yet. Okay, so I'm setting up for your homework assignment, so I'm trying to make it kind of like a step-by-step. Each time we do it, we add one component to it. So instead of doing it this way, which is kind of complicated with all the registers here, I'm going to simplify the design. Okay. In other words, we'll just have the indirect register and the program counter to deal with. the output here can potentially hook up to the indirect register, and then the indirect register can also specify the address. Oh, we cannot ignore the registers, unfortunately, because that's the only thing that can implement a storage so that we can copy a byte to another location. So we can't really quite change that one. We can fix this one and not do anything with it, but we cannot ignore this one either. Okay, so now let's handle this part first. Okay. With this connection, what we are doing, or what we're intending to do, is to say the output of the memory module will go through this trace here and go to the input of the registers. Then we have a way to store what we're reading from memory into a particular register. Is that okay so far? So, but we cannot use this way when information is going in this direction and have the same wire going in the opposite direction from the register outputs. Okay, register output 0 or register output 1. So the way we solve this problem is to use a buffer. Okay, in other words, we can use a buffer and have everything connected to the buffer first. Then we make sure that we cannot have two components driving the bus at exactly the same time. Okay, so whatever component that can drive the bus will have to go through a buffer first. So let me move the component down a little bit here, and we'll break up this line here. In this direction, so we need the buffer to be facing this way. So we go to gates, and then we select a controlled buffer in this case. A controlled buffer, instead of just a buffer, basically means, okay, let me just kind of take one step back and talk about what a buffer is. If you select just a buffer, which is right below the NOT gate, this little component here, the purpose of a buffer is really just to beef up the current. Okay, so it is just acting as what you would expect a buffer to do. It's just beefing up the current and make sure that whatever is driving, it has enough driving ability. So that's the main purpose of a buffer. It can also be used as a delay mechanism because it takes time for the output to update from the input state. So you can also use it for a time delay kind of effect. But it's not useful to us if I cannot control whether the buffer is outputting or not. So we need something that is controlled, so we need a controlled buffer. In this case, a control buffer has to face west because it's going in this direction. And we don't need to give it a particular name in this case. So we'll just go ahead and draw this buffer over here and make connections of the line. Yes, it will complain, because the width of the buffer is only 1 bit at this point. So we can just go ahead and make it 8 bit long, and now the complaint goes away. But what about the other way around? What if we want to take the output of the registers? What if whichever register we have selected, the output, sometimes we want to go in the opposite direction. In other words, in the ideal world, if I want to be as lazy as possible, this is the logical thing that I want to do. I just want the output of the register to hook up to the data bus of the memory so that I can move information or I can copy the content of a register into a memory location. That's what I want to do, ideally speaking. But I can't do that. Okay? I cannot do it because, once again, I cannot have two components driving the bus at the same time. So in this case, I cannot have this straight line here. I have to break it up. And I solve the problem exactly the same way as before. I use a control buffer. But this time it is facing east because the direction is going in this opposite direction. So now the output of one register, and let me see, is it the right one? Yep, output register 0 will go through a buffer to connect to the conductor here, like so. And it's complaining because the width is not matching. So what we need to do is to go to the buffer and change the data width to 8 bits. And now there's no conflicting with problems anymore. All right. So now let's take a look at this diagram and look at a particular trace or a particular node In electrical engineering, this is called a single node. If you look at this entire thing, this red line, all the way down here and all the way across to here, let's take a look at this node here and see if we can still have bus fights, okay, or uncontrolled bus fight, guaranteed bus fight. Do you think we have a guaranteed? Can we have any type of guaranteed bus fight in this case? How so?
If both of the buffers are enabled.
But remember, the buffers are controlled. So a guaranteed bus fight means that no matter what you do, no matter how you control the other components, it will still do a bus fight.
How does the data pin know whether or not it's receiving one or it's sending one out?
You mean the D port of your memory?
Yeah.
You mean this one over here? It's through the control of LD. Because LD, if LD is a 1, then it is driving the D pins. If LD is a 0, no, I take it. Yeah, if LD is a 1, it is driving the D line from the memory chip. If LD is a 0, then it's sampling, which means it's not driving. It's basically just being, yeah, it's an input state. So it's not driving the line. It is in what we call high impedance mode. It doesn't drive current at all. It's just sensing. Okay, and am I sensing a 0 or here, or am I sensing a 1 here? Instead of saying I want to drive this one to be a 0, I want to drive this to a 1. All right, but we don't have a problem anymore because if you look at this particular node here, data can come out, can be active, but it won't fight with this output buffer because this buffer is under our control. Okay, so what we need is a pin connected to this control line here and say, you know what? When the memory chip is driving the line, don't drive this buffer. Okay, make this buffer stay quiet. So then we don't have a problem with a bus fight anymore. Okay. Next question: how should I connect this pin here? What is it related to? If you look at this picture here, is there anywhere in this diagram that pin should be related to?
Read the right.
Yep, the read-write line. Okay. Now, should I connect it straight or should I go through a NOT gate first? Let's think about it. When this line is a 1, the data line will be driving. So that means if I just make a simple connection like this, then I can potentially have a bus fight. Okay. Because, okay, let me just kind of show you the picture here. Okay. When this is a 1, the data line is going to be driven by the memory module. Assuming the select line is also a 1, then this data line is going to be driven. When the data line is driven like this, remember this one here from the right line is also coming to the enable of the buffer. So this buffer will also be enabled. In other words, it will take whatever is on this side of the buffer and output it on the other side. So now we have a bus fight because both the buffer, this one here, and the memory module are trying to drive the data bus at exactly the same time. So we don't want that. So if we don't want this, how do we fix this problem? There's a simple fix to it. The simplest way to fix this problem is to put a negation. Okay, in other words, if it is a read operation from memory perspective, don't drive the line from the memory module.
Yes. Don't we need to drive both buffers off of the read-write pin?
Yes, the read-write pin can connect straight to the other buffer because when we are reading, we're reading into a register. So that it makes sense that the memory bus will be driving, the data port of the memory module will be driving, and then the register one will be sensing. So that one can just be a straight connection, and then the other one has to be a negation because we don't want that to happen. Okay, so we will go through a NOT gate here, and this NOT gate is just always going to be there. And we'll make it a narrow gate facing west, and we'll just put it here. That's a good place. All right. And then this one does not need to be negated. Ah. Let's negate it. There we go. Okay, so this guarantees that between the register module and the memory module, the direction of the data pin is always going to be correct. There are two types of scenario. Okay, the first scenario is when this is a 1, when the right line, when the slash right line, okay, let me just change the label again back to read write, because it just makes it a little bit more clear. When it is a 1, it's a read. When it's a 0, it is a write. So when it's a 1, it is a read operation. But the read operation is seen from the perspective of the processor, not from the memory module. So we are basically reading information from the memory module into a register. So in this case, this line goes here. This is a negation. So this buffer will be turned off. But that makes sense because we are not, the output from the register module should not be driving the data bus. But at the same time, this line also goes here without negation. So this buffer is turned on. That makes sense because this port here is connected to the register input. Are we doing okay so far with this diagram? Okay. So now we have the proper interface between the memory module and also the register module. Now we only have to hook up one of the registers to memory because it doesn't make sense to use both registers at the same time. Because you can only write 8-bit at a time. 2 registers will specify 16 bits. And because the data bus is only 8-bit wide, so you cannot have both going to it at the same time. Yep.
Wasn't one read on there?
Which one?
You have our read write, and I thought when you drove high on there, it was reading.
Yes.
And then when you want the output from the registers to put out information, so
Nope. Because remember, a read operation is seen from the processor's perspective. Okay, I think what is not clear is where's the boundary of the processor, right?
Okay.
What is outside of the processor, what is inside the processor. So let me draw that line here. Let me see if I can just annotate.
reading from the memory.
Right, we are
Not
reading
memory
from the
reading.
memory. Yep. Of this entire design, this module here, the memory module, is the only thing that is outside of the processor. The register module is inside the processor, and as is the other components. So the program counter, the indirect register, and the mux, those are all inside the processor.
Okay.
Yep. That's a good question. I needed to clarify that. All right, great. So we are close to getting everything done. This pin here is the enable of the mux. So, well, we can keep this one asserted at all times. In other words, something is always going to drive the data bus. It's okay, that's not a problem. Because the data bus can be driven at all times, but until the memory module is selected, it ignores everything on the address bus. So it's okay to keep it driven all the time. If you're designing a low power device, then you might want to deal with and say that sometimes you do not want to drive the address bus, just because in order to save power, you don't want a line to be driven. And this brings up something that is also hardware related. How do you make a device low power? Do you do it by not driving something, or do you think that's not going to matter much? What is actually consuming power? Why is your Intel processor consuming 100 watts?
All the extra silicon?
Say again?
Because of all the extra silicon?
Well, it has to do with silicons, okay? But what is actually consuming that current?
Making all the switches.
Making all the switches. Okay, it's
Right. At the transistor level, every time you switch a transistor, it has to
Yep,
use power.
exactly. It has to do with the switching action rather than maintaining the state of a transistor. Okay, let me say that again, okay, because this is somewhat important, especially for those of you who are getting into electrical engineering. It is not maintaining the state of a transistor that takes power. It is the transition that takes power. In other words, if you have a transistor that was originally off, the act of turning it on is what is consuming power. Once it is on and you're just keeping it at an on state, does not take much power. Is that okay so far?
Yeah.
Because that's not intuitive. It is actually counterintuitive. If you look at a switch of these lights in this room, okay, the act of flipping that switch takes a fraction of a joule of energy, right? It doesn't take much for me to click the switch, and yet I can turn on hundreds of watts of power at the same time. So the on state itself is what is consuming power in the case of lighting in a room, your toaster oven, and stuff like that. Okay, the act of switching is minimal. Okay, once the device is turned on, it's consuming a lot of power. That's exactly the opposite when it comes to silicon inside the processor. To maintain a state of on takes literally no power. Well, not literally, but close to no power. But the act of turning it on from an off state is what is taking the power. Imagine something like this. Imagine that I have a switch like those switches in like big, huge facilities, like a lever thing that is the size of myself. Okay, so I have to pull the switch and then click it here. Okay, and what I'm really turning on is a little LED light. Okay, so once the switch is done, keeping the LED light, LED bulb in the lit state is like almost nothing compared to how much energy I had to spend in order to make that switch. To turn it off is the same thing. Now this is really the funny part, is turning off something requires power. Because I need to take the switch, take the lever, and crank it all the way back to the other side just to turn off that little one LED. And of course I'm exaggerating a little bit here, but that's what's happening inside the processor. The reason that it is the case has to do with the type of transistor inside the processor. It's called a MOSFET, which stands for metal oxide. What is the S? Metal oxide
Semiconductor?
I know FET stands for field effect transistor, but I cannot remember what the S stands for. Now I have to look it up. I cannot stand it when I cannot remember something. Okay, MOSFET, metal oxide semiconductor, there we go. So metal oxide semiconductor field effect transistor. It's a really kind of funky long name, but it's a very interesting kind of thing too, because from the hardware perspective, the current to control the gate does not connect to the current that is being switched. Okay. An electrical engineer would actually slap me right now because I'm drawing a picture of a MOSFET, but in a very, very simplified way. So any electrical engineer would look at this and go like, no, that's not how you write, that's not how you draw a MOSFET. But for my purpose, it's good enough. Okay, this is what we call a gate, and this is an N-channel MOSFET. So this is the source, and that's called the drain. Doesn't matter. The labeling is just there. But this is the control voltage. Okay, this is me. This is the switch. This is the lever to turn on and turn off something. This is what is being turned on and turned off. Okay, and to turn on something, this is also a capacitor. When you look at this part here, it looks like is a capacitor because it does act like a capacitor. And as a capacitor, in order to change its state, you have to fight whatever charge is already there, and it's fighting the charge that is already there, that is consuming the energy. Once you switch it, to maintain this at a high or low voltage requires no power because there's nothing that can discharge it. There's a very little current to discharge it. Once it is on or once it is off, and that's why with computers, with processors, it's the switching part that is consuming the power. It's not making something stay on that is consuming the power. And that's also why when you have a processor like an Intel i7 processor, if you want your processor to run cool without using extra cooling equipment and stuff like that, and you tell yourself and say, well, I don't really need all that processing power, okay, because I'm only doing something that is not really that require a lot of processing power. Clocking your processor down it will make it consume a lot less power than the high frequency. Some of you know this already because when you make your own computer, or if you have a laptop computer and you want to maximize the life of your battery, one thing you can do is to clock down the processor and just say, okay, don't even get to the maximum frequency that you can get to. Okay, I'm running on battery here. Unfortunately, the one component that consumes the most power on any type of portable device is not the processor, it's the screen, exactly. And does anyone know why the screen, especially with a traditional LED design, is consuming so much power? What is LCD? I know I'm digressing, but liquid crystal display. That's old technology, has been around for a long, long time, right? But it's very, very, very inefficient. If each vary is doubling, then very, very, very is actually appropriate in this case. Because 2 to the power of 3 is what? 8. So, because what you're seeing, okay, let's say you want to see a white pixel, okay? You turn a pixel to white, which is 255, 255, 255 in RGB, okay? Maximize everything. What you're really seeing from your perspective is 1/10 of the intensity of the backlight of the device. That is the efficiency or inefficiency of LCD.
That's banana.
Yeah. That's why it's consuming so much power, because when you want to see something, even a white pixel, a full intensity white pixel, is only 1/10 of the intensity of the actual backlight behind it. And that's why it is so inefficient, because in order for you to see a quote unquote bright pixel, what is behind it, the backlight, has to be 10 times the brightness that you want to see.
That's because it's a transmissive. You have to fight through the.
It's a deletive process. Yep.
Whereas the AMOLED
It's
is
direct.
emissive.
Yep.
It's much more efficient.
Yep. The LED technology is direct because you're lighting up something and it's going to you directly. But OLED, the organic LED, has a problem of lifespan. It doesn't last as long as
The blues die
LED.
out so quick.
Huh?
The blues on them die out so quick.
Yeah, the blue is interesting because I don't think they have found material that can emit blue directly. So blue LEDs are actually ultraviolet LEDs with fluorescent material to turn the UV light into blue light.
That's pretty cool.
But it also requires a higher voltage. The drop across the diode is actually higher, so that means it's actually less efficient compared to the other frequencies. Red LEDs are super efficient. They're very, very efficient compared to blue. They consume like this much current and will be blindingly bright. Yep.
Wait, so would you make it more efficient if it was all monochrome, essentially?
Correct. Monochrome and using only red, yes.
Like those old Virtual Boys.
You like the what?
Virtual Boys?
Virtual boy.
Nintendo had those little sort of 3D-ish kind of.
Yeah.
Yeah.
If it's all red LED, if you don't mind, reading your entire screen is all red, just different intensities of red. Yeah, that would make it very, very efficient. Or you can use e-paper, e-ink. E-ink is interesting because once you change the state of a pixel, it stays there. Once again, it is the transition that takes power. Once you have made the transition and you just want it to stay at a certain state, it doesn't consume power at all. So that's why with the Kindle, when you flip a page, that's when power is consumed. But when you're just reading a particular page, it's just like very, very little power consumed, if any. No one has noticed that? But we don't want our cell phones to be based on e-ink. Well, actually, depending on how you use a smartphone, sometimes it really doesn't matter. I mean, you can use an e-ink, screen. And I think what can possibly happen in the near future is to have dual screen. So one is e-ink based, for stuff that you don't really need to update it frequently. So when you're not playing games or watching YouTube, you can use the e-ink screen.
Professor Lestrang said the exact same thing.
Really?
Strange pulled it up and was showing us they've got it in Europe. It's a Russian-based company or something.
Yeah.
And I haven't heard of it. This is like, it just kind of popped up in my mind.
Kismet.
Hmm?
Kismet.
Yeah. creepy. It's creepy when Michael can think of something and think of
Well,
the same thing.
Yes, that means it's confirmed that's what's going to happen in the future. If both of you guys think that way.
Oh. All right. Well, enough digression. So I'm hoping some of you enjoyed the digression. I'm pretty sure some of you think, man, another digression. All right. So getting back to this design, I may not be able to finish it today, but I will have to do it. I'm doing it really slow here. Okay. So this port here of the registers is input register select. In other words, I use this particular pin to say, okay, which register is going to be the input register, okay? So that is needed, okay? I need to specify this. So once again, we'll use pins to do it. And this is going to be an input pin. And obviously it's not clock, and it has multiple bits because we have 4 registers, which requires 2 bits to specify which one I want to access. And we'll just use the same name here. Input select for the registers. So right now I'm not too concerned of making this pretty, so I'm gonna put the pins all over the place. Okay, there we go. All right. Okay, so now we have a way to read from memory into a register by selecting which register we want to read into. But we are not quite done yet because we have to specify register write enable. In other words, are we ready to actually write to that particular register? We have to supply a clock to write into that register. And the reset line here, oh, did I delete that line? Yes, I deleted. I deleted the line when I deleted the component. Register 1 select, register 0 select, that's for output. So we want to specify which one is going to be outputting to the output register. So we need to specify that. Register enable 1, register enable 0. So we need to specify the enable as well because we have to say who's going to drive the output. All right, so minimally, we need to have this line selected or specified. We need this one to be specified, and we need the clock line of the write to be specified, and also the write enable to be specified. For simplicity purposes, no, that's not shortcut it. Let's do the whole thing. All right, so now we have to specify a few pins, and they're all going to face east. I'm just going to pop a few pins down first, and then we'll go ahead and change the label of the pins. All right, so this one here is specified, is connected to this pin here, and now use the same name. It's register write enable. So when this pin is okay, so when this pin is asserted, we are enabling the writing or the update of a register. But once it is enabled, you still have to give it a clock, a transition on the clock line from low to high in order for the register to be changed. So then the register actually has the content. On the other side here, when you're outputting, you also need to specify this pin here to specify we are enabling the first register, or register 0, to be driving the output. So this may not be needed after all, because we have this pin here. And then we have the other one to specify which register is going to be register 0, which is going out of this port here. So when you look at this label here, it is enable 1. Oh, I don't care about enable 1 at this point, so let's get rid of this. We just need to select which one is register 0, which is what this particular port is about. So we'll go ahead and have another pin, input pin. This time we have 2 bits, and we'll attach it here. Make it face north, like so, and change the name. It's not clock, it is register output 0 select. All right. One thing to connect to here, that is output enable 0. So we specify 1 p.m. Make it face west. And change that to register output 0. There you go. Attach it here. Okay. I think we're ready to read a byte into a register and then use that register to write to another location. Okay? So let's go ahead and give it a try. First thing we want to do is to specify some content into memory first. Now at this point, we don't have any ability to do that other than just forcing the content into memory. So we'll go to edit content, and let's just pick some random location here. I'll just pick this location here and change it.
Just add it.
Oh, yep, that's it. So we'll put a FA here. FA in hexadecimal is FF is 11111010 in binary, and we want to copy from this byte over to, let's say, this byte over here. Okay, so let's call this byte I don't know, 5D. Okay, and 5D has a bit pattern of 0101 1101. Trust me, once you have done this for a long time, you too will be able to do conversion like that. Base 16 and base 2 are very easy to convert. It's a table lookup. There's no division whatsoever. There's no calculation involved. It's really just literally matching one item to the corresponding item in a table. And the table only has 16 items. All right, so we can probably keep this editor up here or somewhere on the screen while we work on the other one. Okay, so getting back to here. So the first thing we have to do is to read from this location. What is that location? What is the address of that location? This is 2021. That would be 22, location 22. So in order to read from location 22, you can either make the PC go to location 22, or you can use the indirect register to go to location 22. What I'll do is I'm going to use the indirect register here. So we'll go ahead and specify location 22 in the register. So with the register, I think you can just
It's like the finger tool.
okay. So now we can type in the location, which is 22 in this case, and you can see that it's automatically going the output. I think this one is by default turned on, and that's why the output is already there. So this is FA, and we are going to read it into the register. To read it into the register, several things has to happen. The clock line is not involved when you're reading. In other words, this is already driving because the read line is already a 1, the selection line is already a 1. So the memory chip is paying attention to the address bus, and it is also paying attention to the read-write pin. Since the read-write pin is specifying a read operation, it is already outputting that content onto the data bus here. So content is already going in this direction, going through this buffer, and into the registers. Now into the registers, I have 4 registers. I can select one of the 4 registers to store the content. Let's pick a 01 or the first register to store the content. And once we specify the input register, we still need to enable register write, okay, to say that yes, we are ready to update the register, and then use the clock line to actually make it register. Okay. Now that we have done all of this stuff here, we can turn off the write line because the register should be updated already. Now it's time. It's our turn to write register 1 to the other location. Okay, the other location, which is the 5D here, is located at C0, 1, 2, 3, 4, 5, 6, 7, 8. So that would be C8 as a location. So now we have to go back to the indirect register and change that to C8. And you can see that it is going to location C8. And as far as the memory is concerned, it is still understanding this is a read operation, but That's not the case. We want this to be a write operation. So we turn off the read-write pin here. Select is still here, but now in order to, now we have to also go to the registers and say we want the output now, but we don't want the output from register A. We want to use register B because that's where we store the value to begin with. So we select register B, and then we enable register output. So now the register module should be driving this particular line here. And once that line is driven, and this line is also driven, the data should be presented onto the data port already. But the content of memory is not updated yet because we have not clocked it. So once the selection pin is a 1 and you specify a write operation, then you have to clock it in order for that content to register or to be stored in memory. So we have just successfully read, we read a memory content or location into a register, and then we store the content from that register back into a different location in memory. Wow, that took an hour and 15 minutes because I was also making all the components at the same time. But can you guys kind of, at least without referring to a lot of the details, okay, which pin needs to be 1 or 0, in what order, do you see in general how things are kind of connected, how they're glued together? Memory module, okay, which is external to the processor, and then inside the processor we have a register bank. We have, in this case we're not using the ALU, we're simply using the register bank, but we're also using the indirect register to help us decide which memory location do we want to access. So are we doing okay so far in terms of seeing how things are connected and what each component is doing in the grand scheme of things? Are we doing any processing yet? Are we doing any adding, subtracting, doing any type of processing? No, we're not doing any processing yet, but we are doing the basic stuff. At least we now can read and write from memory and put it into registers. I cannot do a single thing until I have the registers containing useful information to process, because the ALU connects to the registers. So I need to be able to go from memory, store something into the registers, and then use the register to supply the information to the ALU in order to process that information. Okay. Now, I know we are running out of time, but I do want to point out one thing. Who is going to be in charge of flipping all these bits to zeros and ones, and turn this on first, clock that one, turn this off again, and then do this and then do that?
Processor, no.
There's another component inside the processor to do that. It's called microcoding. Okay. How many people have seen a music box or the inside of a music box? So what does it look like inside a music box?
It's a cylinder with a bunch of pins sticking out.
Right, it's a drum with pins sticking out, and the pins, plug.
And as it turns around, it hits a certain level, 12 times or something like that.
Right.
And that creates the sound effect as it clicks.
Exactly. So what we need is something like that, except it's not making sound. It is flipping the bits, all of these selection pin, enable pin, and whatnot. It will flip those pins to on and off, in a particular order. Okay, that is what we call microcoding. So before I end today's lecture, which is a pretty good time to end today's lecture, you won't have any homework assignment, but you should. I will make this file available so that you guys can play with it. Okay. So what I want to do is to go to YouTube, and we want to look at a music box mechanism. Here we go. There we go. Memory. Do you see how the little pins? Do you see how the little pins are making the sound because it's playing the quote-unquote harp here? And each time a pin goes under a particular pin, it basically makes a sound because it just plays that little thing. So imagine that we have something like this, except they're not necessarily pins. Some can be an entire ridge, which means it will hold this pin high for a period of time, while other ones are transitioning.
Like a Guitar Hero?
Like a what?
Guitar Hero?
Like a what?
Guitar Hero?
Yeah, yeah. But I'm not a guitar player, so that doesn't pop up in my mind. But just like that, okay? So we are now trying to do something like this, okay? So instead of having me, to interactively click this line here, click this line here, click this line here, we want it to be automated. We want something like this and say, oh, we want to read from a location, play that tune. We want to store to a location, play that tune, okay? That's called microcoding. Okay, because we are basically making, we're gluing everything together. Okay, we're trying to make it glued for everything, not only in terms of circuit, but also in terms of timing. Okay, when do we do what in a sequence? Okay, so that's what we'll do next Tuesday. We won't have any class on next Thursday. I'm taking Thursday off, so next Tuesday we'll be here, but next Thursday we won't be. So if this is the only class you come here for, next Thursday you don't have to come at all. All right. So I'm going to upload the file, and then you guys can go to the lab and play with it and ask questions if you have any.